Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to welcome Emery Kuchiman from Stanford University.
Hi. Thank you. My name is Emery Kuchiman. I'm graduating from Stanford University this year, and I'm here to talk to you about using statistical monitoring to detect failures in Internet services. So the problem I'm going to focus on today is that of Internet services failing. This is a serious problem where greater than 60% of sites, according to recent surveys, have user-visible failures. These are otherwise well-run sites, and what ends up happening is that when they go down, they lose money, depending on the size of the site and how much money they make. They can lose anywhere from hundreds of thousands of dollars to millions of dollars per hour. So this is not just a problem that affects lots of sites, but also one that affects them severely. From the human side, when these sites go down, it's also a big pain for the people who are actually running the site. At 2 a.m., the site goes down. Everyone who owns some part of the service, up to 20 people, are going to be woken up to check their pieces of the site and fix any problems that they might see. I'm going to focus on one particular type of Internet service failure, an application level failure. These are the types of failures that are the hardest to detect at these services. They don't show up as obvious problems like a machine crash or something that an operator would be able to notice outright. Instead, it's a failure that the customer can see, but the operator can't. The service is still running, but the application is doing the wrong thing. Detecting these types of failures, in particular, accounts for 3/4 of the time to recover from these failures. So one specific example that I've heard about is a problem where it took 6 hours to realize that the site was down. But then once they realized that there was a problem, they were able to localize the problem and detect it and fix it within 2 hours. The approach I'm going to talk to you about today is that of looking at the structural behavior of the site, how the site is interacting with itself within the service, and then applying statistical monitoring techniques to detect anomalies in these behaviors. I'll talk to you about some results we have from testbed experiments and early results from deploying some of these ideas, Amazon.com and another large internet service. Let me go into one specific failure that I've run into myself. This is a US Airways website where the application is supposed to be showing people their flight itineraries, letting them buy flights, etc. My wife bought a flight, a couple years ago now, and she sent me her itinerary right up. And if you look, this is the page where the itinerary is supposed to be displayed, but there's actually no itinerary information here at all, no flight information. It's obviously doing the wrong thing. The only detail is that on Friday, October 10th, the status of this flight was confirmed. But this ticket has nothing to do with October. It was bought in March for travel in April. So there's obviously a problem going on. And in case you can't tell, there is no other button to click on to take you to the real itinerary. This is where it is supposed to be showing up. But if you're monitoring the site appears to be up. The machines are all live. Heartbeats and pings aren't going to give you any errors. The HTTP and HTML isn't giving any errors, and the HTML is valid. There's no performance problems. This site comes up very quickly. All looks okay. But there is a failure. The key is that it's a failure if a user notices a problem, it's not just a problem of crashes. The challenge to detecting that type of failure is that it's really difficult to specify what an application is supposed to be doing at the high level. These semantics are at the human level, not at any easily quantified machine level. You can't just say, this page should always return 1 or 0 on success or failure. The problem with, additionally, anticipating all the different types of errors, so enumerating what could go wrong isn't an option either. There's too many things that can go wrong. And requiring a specification, even if we could write it once, would be a maintenance nightmare just because the application changes rapidly enough and often enough that you'd have to rewrite the specification, and that would be, in itself, very difficult to keep up to date. So the approach I'm going to talk about is one where we accept that we don't fully understand the system and look to detect problems without any a priori specification of what the application is supposed to be doing. What goes on today in detecting failures? Well, talking to internet services, we've been able to classify the types of monitors that they've deployed into 3 different categories. One is these simple low-level monitors, the heartbeats and pings, where you try to detect the crash or liveness of the machines behind a service. And these detect lots of failures, but they miss the high-level failures. That's why these application-level failures are right now the types of failures that take the longest to detect. The second type of monitor that we've noticed people using are application-specific monitors where someone has hand-coded something. So you know, for example, that people really want to use a search functionality in your site, so you've hand-coded a test to say, okay, I'm going to send in a search request to this site, and depending on the results back, I'll actually know whether the service succeeded or failed. The trade-off is code complexity and maintainability. You have to embed the knowledge of how your application is working into your test suite. There's a code coverage problem here because you can't test all the functionality. And in addition, if your application changes, which it will, you have to make sure that you change these application-specific monitors as well. Because if you don't, your application-specific monitor will either generate false positives or false negatives. It'll miss failures. The third type of monitor that we found deployed, and this is actually one of the more interesting ones, is monitoring business metrics directly. So for an e-commerce site, this might be something like dollars per minute. For a search engine site, it might be searches per second. These catch high-level failures when they affect the business metrics that a company cares about. And in this way, they really do a good job of catching the important problems at a site. But by the time they've detected a problem, a drop in the dollars per minute, the failure has already affected the business itself. So that can be too late. We want to detect problems earlier if we can. The key point is that none of these monitors are good enough. Right now, the technologies underlying these monitors force us to make trade-offs, trading off functionality, trading off the complexity of the test suite and the maintainability of the test suite against its ability to detect application-specific problems. The ideal monitor would combine the strengths of each of these and let us detect high-level failures, have low complexity and easy maintainability on the monitors, and also detect them rapidly enough that we can fix the problems before they affect business metrics. This is really, stepping back a little bit from this problem, this is the problem of detecting failures in internet services is one instance of a much broader, more important problem, and that is that we don't understand the larger and more complex systems that we're building today. This makes management harder and dependability worse. And I think that really the issue is that we can ask any question we want about how these services are running, but we can only ask it at a very low level. We can ask any question we want as long as it's a low-level question. And all these details are overwhelming. And really what we care about is a high-level question. Is it working? We don't care what the CPU usage is at any one machine. And those high-level questions are the hardest ones to answer today. We don't have a big picture idea of what the system is supposed to be doing. So in a broader context, the goal of my research is to bridge the gap between these low-level behaviors that we can observe and the high-level questions that we actually care about. In this particular talk, I'm going to be focusing on one instance of that, the fault detection process, where we're taking low-level observations and translating them into high-level, into the answer to the high-level question of, is this service running or not? So in a nutshell, the problem I'm talking to you about is improving availability by detecting more failures automatically. So this better detection should give us a faster return to service when there's a problem. I'm going to focus on application-level failures, the ones that are the hardest to detect today. This is a relevant problem because poor detection affects lots of services and affects their availability and their viability as a moneymaker for the companies that run them. It's challenging because it's just plain difficult to detect failures without having a specification or an idea of what the service is supposed to be doing in the first place. It's unsolved. Existing monitors are inadequate to the tasks we saw today. And it's an important problem because it's just one example of a broader management problem with the large complex systems we're building today. So I've done quite a few different pieces of the fault management problem, worked on a few different pieces of the fault management problem in my work. So all the way from inferring system structure to detecting failures, to localizing a failure. Where is a failure in the system once we realize that there is one in the system? And then using this information to trigger recovery. I've done this work across various levels, various different kinds of systems, from the Windows registry to detecting failures and localizing problems in a clustered hash table, to working with J2EE, a middleware framework for internet services, to working with Amazon.com and another large internet service provider. What I'm going to talk to you today is about my work on fault detection specifically. And I'm going to concentrate most of my talk on fault detection in the context of J2EE. And then I'll give you some early results from how we're applying this at Amazon.com and one other service. So we've talked to you about internet service failures. What I'm going to talk to you now, over the rest of the talk, is about the types of structural behaviors that we're monitoring and why I believe that these are indicators, why these should be indicators of failures in sites. Secondly, I'll talk to you about statistical monitoring, how we actually monitor these behaviors and determine that they are behaving anomalously. Then I'll talk to you about some of the evaluation work I've done and wrap up the talk. So what do these internet services look like inside? Let's start to dig in a little bit deeper and talk about some of the behaviors that we're going to be monitoring. A typical 3-tier internet service has, on its first tier, a set of HTTP front ends. These are like web servers. They're open to the internet, and their primary responsibility is managing the presentation layer of the data that is being sent out. So they basically put the information that the user is supposed to see into a pretty packaging and send it off to the user. The middle tier, the application components, is where the bulk of the processing, the application logic, and the processing of these requests goes on to. And in the third tier, we have a database tier where persistent data is stored. So when a request comes in to a service, it hits one of these web servers. That web server will forward it on to a set of components in the application logic in the middle. These components will talk amongst each other to get the right functionality done based on what the request is. Some of these components will talk to the database, pull out information, change information in the database, etc. Then that data will get basically returned to the user back through the HTTP front end. So what does one specific request look like? So I'm going to talk to you about one request that we've pulled out of Pet Store 1.1, which is one of the applications we've worked with. It's an e-commerce site. And the request I'm going to highlight right now is a checkout request. So a user has been shopping around the site for a while. They've put some items into their shopping cart, and now they want to finalize the purchase and leave the site. So the checkout request comes in from the internet and hits the web server. The web server then decides, okay, this is a shopping-related request. I'm going to talk to the shopping client controller. They're going to handle doing the functionality behind this checkout request. The shopping client controller then says, okay, if this user wants to purchase these items, the first thing I need to do is talk to their shopping cart and pull out the information about the items that they have in their cart. The shopping cart service now goes and says, okay, I need to return the information about these items. Let me talk to the catalog component, and the catalog component will give me the descriptions and things and read those out of the database. This is all returned to the shopping client controller, who then says, okay, now I know what this customer wants to buy. Let me check the inventory at our site and make sure that these items are actually in stock. And that happens. And then finally, the shopping client controller says, okay, everything is good. Let me then forward this to the customer component and have that send along this item information along with billing addresses and shipping addresses, and have that forwarded off to the ordering component, which will then put a purchase order into the database, and the request is now complete. The key idea here is that the granularity of the components that we just saw and their behavior is tied to application functionality. And this is a function of how these components are written in most internet services today, both because of software engineering concerns and because of scalability concerns. We're going to take advantage of this and basically watch this structural behavior at this granularity. And when this structure changes, we're going to say, because the component granularity and this behavior is tied to application functionality, when it changes, we're going to have some idea that the application functionality being provided to the end user has also changed. Yes?
Is this stuff what we had a column labeled first system structure? Is this what you mean by system structure?
Yes. Although the work that I meant when I said inferring system structure comes from other systems where it's not as easily laid out as this. So for this, I just believe that this is just observing it. The inferring system structure is doing some more analysis to pull it out when it's not as obvious. Mm-hmm. And so basically, when a change in functionality affects the behavior of one of these components, we're going to say that not only is it a change in internal behavior, but it also affects a change in the user's behaviors, in the behavior the user is seeing as well. So my approach to detecting failures is going to be to monitor this internal behavior, and when there's an anomaly, say that, okay, something has changed and that's possibly a failure. Which behaviors exactly I'm going to monitor? Well, that's a good question. We're going to want to choose a behavior that's likely to change if and only if the application functionality changes. And we want to monitor behaviors that are tied to units of failure that someone cares about. Either the user cares about or the system cares about. And so in the next two slides, I'm going to talk about two structural behaviors that are easy to monitor and therefore easy to deploy. They're going to be behaviors that do reflect application functionality, and we're going to catch failures that find failures when the system is affected and not necessarily just the business metrics. So the first behavior is a relatively simple one, component interactions. So what I'm going to do is monitor all the requests that go in and out of a particular component in the application. And basically, things like the function calls in and out of a service. The second behavior is a complementary one. While the component interactions monitor how a specific component behaves as many requests flow through it, the second behavior I'm going to look at is how one specific request flows through a system across many components. So it's an orthogonal slice of the system structure. And we call this path shapes because it follows the shape of the path of a request as the request flows through the service. So now I'm going to talk about how we actually model and detect anomalies in these two behaviors. So the challenge to monitoring is to find a way to first learn what the probably correct structural behavior is, and then we're going to use this to detect the incorrect behaviors. The first challenge is how to actually build this probably correct model. How do we capture the correct behavior, and how do we model these behaviors such that we can use the model to detect anomalies? And the second challenge is false alarms. What do we do, and how do we deal with a detection system that might generate an alarm when there's nothing actually wrong with the system? So I'm going to tell you about how we avoid some false alarms by, say, factoring out workload variation, and how we mitigate others. And an important note, I am not a statistician or a machine learning expert. I use some tools, but I'm not going to complain. I'm not going to make an argument that these are the best algorithms or so. My goal is to just show how the machine learning types of algorithms can be applied to this problem. And I hope machine learning people who actually know what they're doing in that field can then dig deeper and find the right algorithms. So the first challenge, how do we capture probably correct? So what we want really is a baseline model of the acceptable patterns of behavior within a site. It doesn't have to be perfect, but we do want it to basically draw a approximately correct envelope around the correct behaviors that we might see. The time to capture this acceptable behavior is an important question. And it depends really on how quickly the site's functionality is exercised. So if you have a relatively simple e-commerce site with lots of workload coming at it, then within a few minutes you might expect to have seen all of the important functionality at the site. A more complicated site, perhaps a brokerage site or something that might have varying patterns of behavior throughout the day, that would take a longer period of time to capture all of the acceptable behavior at the site. But the key is that we're going to build this baseline based on monitoring the site in real time. So we're going to monitor the site, and from what we see it doing, we're going to build this baseline. So we're not going to try to dig into the code and do an analysis or a static analysis of the baseline. There's two different axes along which we can actually build this baseline compared to the rest of the system. The first is a pure comparison, where we assume that most of the system is working correctly. And here, we look at, say, all the replicated components behind the system and say, well, there's 100 software components that are supposed to be doing the same thing. Let's look at their majority behavior and say that that their majority behavior is actually correct, and use that as a baseline to detect problems in any one of the components. So if we say, notice that 1 out of 100 components, or 2 out of 100 components isn't doing the same thing that the others are, then we would say that we've detected a possible problem in those components. This detects problems affecting part of a site. Even if that problem has been there for a long time, it doesn't detect a problem that affects the whole site all at once, because your average behavior then is incorrect. The second degree along which we can build a baseline and detect failures is the time comparison. Here we assume that most of the system is working, that the system is working most of the time, and we'll build a baseline based on the behavior of the system over time. We'll take snapshots every few minutes. And in this case, we can detect failures whether they affect all the site or not, as long as it's at some time previously the system was working correctly. These two types of baseline models are complementary, and the best way to use them would be to use both of them correctly. So build up more baseline models. How do we actually represent the behaviors that we're talking about in order to detect anomalies? Well, for the component interaction model, what we do is, for the component interaction model, what I do is represent the interactions a component has with the other components in the system using a set of weighted links. So here, each arrow on the left in the baseline pattern represents a particular set of interactions that are coming to this component that we're looking at from another component. So from the top left we'd say, for example, 40% of the interactions of this component are coming from there. 10%, say, are going to the component off to the bottom right of this one. And what we'll do is, after we have this baseline model that we've observed the proportions of these interactions over time, we then take another look at the behavior of the component right now and compare these proportions using a chi-squared test of goodness of fit. And this will raise an alarm when there's a statistically significant anomaly, when the odds of both of these numbers having been generated from the same underlying process is low.
Question?
Yes?
So these are, you're not making any attempt here to say a particular message, the checkout message coming in on the top left should send an inventory message out or advance.
No.
You're just adding up total numbers.
Yes, that's correct. And so the unit of failure...
Certain sorts of failures. That's going to miss some.
Yes. So in this particular case, what we're looking at is this component failing or not? And then for your checkout request, then, we'll look at the path shapes. So really the units of failure are complementary. Here it's the system's unit of failure is the component. And then the path shapes that we look at are tied to the user's unit of failure. Did the request succeed or not? So in the case of this particular message came into a component and didn't do the right thing and left, that would be something we'd hope would show up in the context of the path shapes. True. Mm-hmm.
So each component using the chi-square test. Now the chi-square test is now seems to me like the number of arrows pointing in and out of the node.
Yes, so we take...
Same threshold for every node?
We adjust it appropriate to the degrees of freedom. Mm-hmm. So now on to path shapes. How do we model path shapes? Here, what I do is build up a probabilistic context free grammar to represent basically when a path enters into a particular component, what are the odds of it calling that set of components or that set of components? What are the odds of the different types of behaviors that we might see within this component? So, for example, here, there's two sample paths that I've drawn up on the top right, where in one path, component A calls B, calls C, and another one, component A calls B and C directly. So here, you can learn the probabilistic context free grammar representing those two paths and ask the question, okay, a request has entered component A. What are the odds now of it calling B versus what are the odds of it calling B and C together? Then what you can do is use this probabilistic context free grammar to assign anomaly scores to incoming path shapes. And if these incoming path shapes look very anomalous according to the grammar that has been learned, then you can say that there's a possible failure. Now, just a note, normally probabilistic context free grammars are used in the context of natural language processing and use them to assign a probability score directly to a particular sentence or parse of a sentence, rather. That has a bias against long sentences that is appropriate in the context of natural languages, but not necessarily appropriate here. So we had problems with that. And so I actually ended up developing a separate anomaly score that uses the values of the probabilistic context free grammar. I won't go into the details here, but perhaps if there are questions, then perhaps we can talk about it offline or after the talk. So once an anomaly score has been assigned to the incoming paths, what do those scores look like? So here on the left is a histogram of the baseline distribution of the scores assigned to each of the requests coming into a system without failure. So the y-axis here is the number of requests being assigned a particular score, and the x-axis is the score itself. And you can see that when there's no failures, the scores get assigned scores very close to 0. And actually, most of the scores do get assigned to 0, and it goes way off the top of the graph. But it's very left-weighted. This graph on the right now shows what the distribution looks like when a failure is injected. So here the green paths are the successful requests, and the red ones are the unsuccessful ones. And you notice that the red ones are much further out from 0 than the green ones. And so in this case, what's happening is the faulty requests are changing the tail of the distribution of this histogram. And so what I do then is look for a change in this histogram, and when the tail changes significantly and passes some threshold, we'll raise an alarm and say that there's a problem. On to the next challenge in monitoring these behaviors. So there are going to be false alarms in this system due to problems that aren't associated with a failure. For example, the behaviors that we're looking at, really it's the behavior of the whole system, and one of the key factors in how the system is behaving is what the users are actually asking the site to do. Obviously, a checkout request is going to look very different from a search request or a post a comment request or look at my email request. And if the users suddenly shift their behavior from one to the other just because of time of day or just who knows what, a sale, then this change in the workload could cause the behaviors we're monitoring to change in a significant way and cause anomalies. So the solution is that I noticed that, well, we're looking at these request traces and we have end-to-end information on what specific type of request caused a behavior inside the site. And so then what you can do is bin these behaviors by request type and build a baseline model, basically build one baseline model for all the search requests, build a separate baseline model for the checkout requests. And what happens here is that this factors out workload effects. If you get more search requests or more checkout requests, that's going to be okay because you're looking at each one in isolation, each type of workload in isolation. And you can apply this to both component interactions and to path shapes as well. Yes? So Generically, what I do in my system is simply use the URL as a request site. So the URL comes in, and it has some address there, and we can use that. This is simple and has the advantage that it's relatively application generic. It doesn't work as well as a technique where if you knew what your application's request types were. So, for example, you could also use cookies, URL arguments, and start to write an application-specific generator as well. But this certainly does factor out a lot of the important stuff just by itself. Now, factoring out the workload variation works great, but there are still other false alarms that will happen. So these statistical techniques will make mistakes, and I put mistakes in quotes because really it's not the statistical techniques themselves that are making the mistakes. They're just doing the best that they can under a situation where we don't have perfect knowledge about what the system is supposed to be doing. They're doing the best they can, but they're not always going to give the right answer. Secondly, there are going to be significant system changes that aren't failures. And these will appear anomalous. If you have a major feature upgrade to your site, for example, the behavior of it is going to change. And that will show up as an anomaly here. The key thing to notice, though, is that these false alarms are only bad if the response that's taken in response to them is either costly or unsafe. So the way to mitigate this is to find ways to make these responses safe and cheap. So in the case of statistical false alarms, what we do is combine this detection with a safe, fast response, micro-rebooting. This is work done by one of my group mates, George Candea. And what happens is that by having an automatic end-to-end recovery system that responds to failures very quickly and tries to fix problems within milliseconds, then the cost of a false positive is very low. This means that there's also the potential to tune the detection knob away from minimizing false positives and instead focus on avoiding false negatives. So if a false positive is tolerable, then you can start to tolerate more of them and tune your knobs appropriately to make sure you don't miss any failures. We've tested these ideas, this idea of end-to-end recovery in both our J2EE testbed and also 2 clustered hash table prototypes. The second type of false alarm are these significant system changes. And really the response that you have to take here is to retrain your models and rebuild your idea of what the correct working of a system is. And retraining takes on the order of minutes, and the human effort is minimal. Basically, a human has to push a button and say, I made a major change to the system. And then the algorithms start monitoring the site again dynamically and building up a new model of the system.
Something's wrong, right?
Mm-hmm.
So how can you miraculously something's wrong?
That goes more into what micro-rebooting is. So micro-rebooting is basically the idea of rebooting the system to clear out soft state, memory leaks, things like that have started to cause a problem. And that type of problem does account for a significant portion of failures. And what the idea of micro-rebooting is to minimize the time to actually reboot by restarting a smaller set of the system. So a single component within a larger Java virtual machine within the whole system. And so that actually takes on the order of hundreds of milliseconds. It's safe if you structure your system correctly. It doesn't lose data. And you're back up and running really quickly.
So if there's a part of it, which of the many components that are involved
Mm-hmm.
do you choose to reboot?
That goes on to a second stage of my work, which is fault localization. That's probably something we should talk about offline. So now, let's talk about evaluation. So I'm going to talk to you about is both our controlled testbed experiments and also results from these large internet services. So the first thing I did is build Pinpoint, which is the name of our prototype statistical monitor. So I'll refer to the name Pinpoint over the next couple of slides. The next thing is to take an internet service and try to build one that we can actually monitor and pull these behaviors that we want to watch out of a running system. So what I did was instrument JBoss J2E. J2E is a relatively well-deployed standard for internet services. It's popular particularly in some financial institutions and banks and things, and is being used more and more in more and more sites. JBoss particularly is an open source implementation that we could then modify the source code to. It's had millions of downloads and real deployments at Fortune 500 companies and everything. So this code is we're working with basically a real system is the point of this. I modified the system to track all accesses to EJBs and JSPs, which is the application component and presentation layer components within the J2EE. And I've also modified the HTTP server, the RMI protocol, the Java database connection protocol, and the Java naming server protocol to capture the interactions that occur between machines at a J2E deployment. There is a performance hit in our prototype that's relatively significant, a decrease of 17% of the throughput. Now, one can argue that that's a trade-off that one would be willing to make in order to detect failures at a site more rapidly. There are also commercial instrumentations that exist right now that give you the type of information that I need, and these commercial products have already been deployed and are running live on real sites. So I think with the right type of engineering, the instrumentation hit on performance becomes quite manageable. On top of our instrumented middleware, I've deployed several applications, PetStore 1.3 and PetStore 1.1. These are different instances of one of Sun's e-commerce site demonstration applications. And these two versions are actually architecturally different enough from each other that I count them as separate applications for the purposes of this testing. I've also deployed Rubus, which is an eBay-like auction application developed by Rice University, and ECPerf, which is a performance benchmarking application for this system as well. The workload for the PetStore applications is based on a TPCW workload mix, basically trying to balance the number of heavyweight and lightweight requests that go into a site, how many of them access a database or just the front end, etc. And Rubus comes with its own workload generator that gives you a nice distribution of requests. Now, of course, when we run Pinpoint and try to monitor failures, we want to apply some sort of fault load. So here I'm going to talk about what types of faults we inject into the system. And here our goal is to test the application behavior under a range of scenarios. So on the one hand, we look at declared exceptions and undeclared exceptions. These are the Java exceptions that, in the declared case, are actually explicitly written out in the method signature. So here you hope that the programmer is aware of the fact that this exception could happen and has built some sort of mechanism to degrade gracefully basically do the right thing in the presence of these exceptions. Undeclared exceptions are the things like null pointers or out-of-memory exceptions, which, because they're undeclared, perhaps the programmer is expecting them, and perhaps they're not. And in this case, they might not actually, the application behavior might not adjust automatically to these types of problems. Taking that to an extreme, this idea of looking for something that the programmer is going to be anticipating or not anticipating, I also look at omitted calls, where we intercept a request to a specific component and then return null right away. And this is something the application is really not likely to handle at all. And the goal here is to try to find the range of things where an application, how an application might change its behavior in response to a failure. We've also looked at source code bugs and other failures, such as data corruption, overload of the site, etc. Now, one thing that I did not test in my experiments explicitly was bit flips and low-level hardware failures, disk errors, and things like that. We did do some experiments in our group, but these types of low-level failures in the Java context ended up manifesting themselves as either exceptions, where a JVM would coerce a disk error into an I/O exception at the Java level, or as a total crash of the JVM. And the crashes are already easy to detect, and the exceptions are things that we're already explicitly injecting into the system. The last part of the system is to actually verify that this failure actually occurred and look into what part of what requests actually saw problems in response to this failure. And so here what I do is capture all the HTML output coming out of this server, canonicalize it to remove some of the random variation, and then checksum this output and compare it to previous runs where we've not injected failures, and double check that the exception or the low-level fault that we injected actually did cause some problem with the site. So what is the experiment I'm going to focus on right now is fault detection. And basically, the methodology at a high level is to inject a fault and see if we detect it with pinpoint. First thing we're going to do is capture a baseline from a hand-tested system. Here, I apply about 5 minutes of workload to a site, about 1,000 requests, and use this to build up the model of what this particular application we're looking at, how it should be behaving during normal runs without failures. Then I inject a fault and capture 5 minutes of observation of the system under this behavior. Compare this behavior to the baseline, and if it's anomalous, then say we've detected this problem. Repeat this for basically the different types of faults that we're injecting and all of the different components in the system in both PetStore 1.1 and PetStore 1.3. The comparison point that I'm going to compare our monitors to is these HTTP and HTML monitors. These are simple application generic monitors where the HTTP monitor is looking for signs of error in the HTTP protocol. So say HTTP is returning a server 500 error, for example. And the HTML monitor is looking for obvious signs of errors or exceptions in the HTML document itself. So something like the application is printed, say, an error message in the text. That's what this would detect. We also ran other point experiments with different configurations, a clustered setup, different applications. Also injected various other failures, naming server corruptions, overload, source code bugs, etc. And looked at comparing our techniques to two other monitors, log monitors and exception monitors. Problem with these other monitors was that they had a very high rate of false positives. They were almost always generating some problem. The exception monitor in particular, for example, during a 5-minute run without failures would still see tens of thousands of Java exceptions just occurring normally. So neither of these monitors are things that I'll talk about in the rest of the slides just because of their high false alarm rate. I also ran some experiments to see how we could test for false positives, trying to make an extreme workload variation or minor software upgrade, and basically trying to push the limits of what types of normal changes might cause anomalies. So the results of our fault detection are shown here. This bar graph shows the miss rate for our individual monitors. So the lower the bar, the better. The y-axis here shows the percentage of failures that were not detected. And along the x-axis, we have the results from our different types of monitors. And we see here that the pinpoint monitors, the path shape and the component interaction monitors, did much better than the HTTP and the HTML monitors. Now, the path shape monitor did the best overall. It missed the fewest faults, but the component interaction monitor did detect some failures that path shape did not. So they are, as expected, a bit complementary. Now, important note: in these experiments, none of the monitors actually generated any false alarms. So we can compare these results directly without taking into account any other false alarm information. Yes? In the back?
The first two any that the last two didn't have.
No. Yes?
So, as I read the key, the left two bars are applications, and the right three bars are kinds of fault injection.
Yes.
So I
So what this graph is trying to show is, okay, we had some set of faults that we injected into two different applications, and depending on how we divide up those results, we want to see if whether the monitors are application end up being application specific for any sort of reason, if they do better on one application or another, and whether they do better on one type of fault or another. So, for example, we see that the component interaction did much better with PetStore 1.1 than on PetStore 1.3.
This is across all kinds of faults.
This is across all kinds of faults, yes. And in that particular case, actually, the component interaction's weakness is components that are not used very frequently. It doesn't, where within a monitoring period of 5 minutes, they don't, within a monitoring period of 5 minutes, they don't see enough behavior to build up a good model, a statistically significant model of what's going on. And PetStore 1.3 has a lot more components than PetStore 1.1. So 1.1 has something like on the order of 10 to 15 components. 1.3 has on the order of 40 components. And more of those 40 components are actually things that aren't used very often, used very rarely. So in that case, the component interaction didn't do as well. Now, you can say, well, what happens, and this is related to the question in the back, what happens when we combine these monitors? And so here we have a comparison between combining the pinpoint monitors together and combining the HTTP and HTML monitors together. And in this case, we see straight off that using a pinpoint monitor instead of, or in addition to the HTTP and HTML monitors, reduces your miss rate by 30 to 70%, depending on what type of fault you're looking at. And in particular, it is important to note that not only does pinpoint have a better rate of fault detection, it's also strictly better. So no fault was detected by the HTTP or HTML monitors, but not by pinpoint. So in the real world now, how did this work out? How did this failure detection work out at Amazon.com? Now, in the case of Amazon.com, I'm monitoring logs of component behaviors. It's not exactly the same type of analysis that I'm doing in J2EE, but it's approximately correct, approximately the right idea. The additional challenge we had at Amazon was that I don't have component type information. So a particular host name comes in, I don't know whether this host name is supposed to be the same as another host, for example. And what I've done in this case is looked at logs from several severe failures where Amazon has said, okay, we had a problem yesterday, here's the 4 hours of logs bracketing that problem. And some of the types of failures that I've seen are network outages, load balancer failures, database outages as well. And in each of these cases, our analysis did show significant anomalies during the failure. So it's something that our analysis would have noticed. And there's two advantages that I've seen so far. One is that the pinpoint monitoring allows us to detect a variety of failures without any special rules or configuration. So it doesn't have to know how the system is set up. And across all these different types of failures, we didn't need any special configuration or tweaking. It just, by looking at these component interactions, came out automatically, in a sense. And in one case in particular of these failures, we detected the problem significantly early. So in this case, there was a failure that hit Amazon for 20 minutes, and the pinpoint analysis detected the failure 5 to 10 minutes early. So basically, pinpoint noticed the problem 5 to 10 minutes before they did. Once they noticed it, it took them 20 minutes to fix the problem. So a 5 to 10 minute head start could have been quite significant. At the second large internet service that I've applied this to, we used quite different algorithms. So not something I've talked about today, where I've actually monitored non-structural behavior, which is similar to some of my other work on monitoring failures in the clustered hash tables. Here I'm looking at quantitative statistics, looking at the response time, the queue length, etc. at these at the various components in their system. And here we've had success detecting a variety of failures again, hard drive being full, network bandwidth being hogged, etc. And these include failures that were not noticed by their existing performance monitoring techniques. We learned two lessons. One is that not all of the quantitative statistics that we can analyze are useful for anomaly detection. Some, such as virtual memory size, even when they're completely off, are not an indication of a problem. And two, that in this particular site, bimodal behavior is quite common. So we have a specific type of component, and we think that it should be having some normal range of behavior. It turns out that it's actually perfectly all right for it to have one of two behaviors. It's running correctly and it's doing something, or it's not running at all and it's not having any workload sent to it. In this case, what's happening is they've put out, say, 10 new machines, and they haven't told the load balancer about it yet. That'll happen at the next, say, configuration push in 30 minutes or so. So in that case, a large chunk of the anomalies that we were seeing were this second type of failure, second type of behavior, where the load balancers hadn't been told about this yet. Now, taking that into account then, looking at the other types, the other anomalies that we saw, we did detect these failures. So let's wrap up. What are the takeaway points? I think there's several different things to take away from this work. The first is that looking at the coarse-grained structural behavior is a good way to start analyzing application functionality, even when we don't know what the application is supposed to be doing at a high level. The use of statistical techniques together with dynamic observation lets us start to make sense of this complex large system in lieu of an application specification. So without having an a priori specification, we can still do useful things and start asking useful questions based on monitoring and dynamic observation. In lieu of knowing what is actually the correct behavior of a site, assuming that most of the system is working correctly ends up being a reasonable proxy for actual correctness. And finally, these techniques all together allow us to develop an application-generic fault detection system. And together with the fact that we can instrument the middleware without changing application code, lets us monitor for a variety of failures in a variety of applications without any special configuration. There's lots of related work. I'll go over this quickly. A highlight here is the MagPi work being done here at Microsoft Research, and the Project 5 work being done at HP Labs. Now, the main difference between my work and this work is that the MagPi and Project 5 are both focusing on capturing and modeling the behavior of a site at kind of a performance level. And they're not necessarily looking at anomaly detection to detect these types of application level failures. There is other work on using anomaly detection for inferring failures. The metacompiler at Stanford is looking at inferring code invariants at a lower level in source code and looking for deviations as a sign of bugs in the code itself. Deduce and Daikon at Stanford and University of Washington look at dynamic invariants. What value does this function always return, for example? And looking for anomalies there to deduce the fact that a software bug might have manifested. And lots of applications in machine learning, industrial process failures and stuff. The specific difference here between this work and my work would be the level at which we're applying anomaly detection, the specific behaviors and types of failures that we're looking to detect. Other people have also looked at applying other statistical learning techniques to other parts of the failure analysis process. So, for example, Ben Liblet at Berkeley is looking at correlating code level observations to process crashes. And Mike Chen is also at Berkeley is looking at using decision trees to localize failures at eBay. In this case, the main differentiator is the stage of the fault management process that they're looking at. So both Ben Liblet's and Mike Chen's work assume you've already noticed a failure and you have labeled data over what is correct and what is incorrect behavior. I've been focusing mostly on fault detection where you have unlabeled behavior and you're trying to notice whether any one of these behaviors are wrong or correct. And third bullet, NEC Labs has actually taken our pinpoint work and is building on it to look at alternatives to using a probabilistic context free grammar to detect anomalies in the path shapes that we're looking at. So they've actually done exactly what I want, where they're machine learning experts and are starting to dig in deeper for alternative algorithms that can improve on the PCFG. Now, for future directions, I want to step back and look at the broad problem again. I want to apply machine learning techniques to make systems easier to manage and more dependable. So start looking at other problems in statistical monitoring. What other big questions do people care about when they're managing these systems at a big picture level? And start to apply statistical learning techniques to answer those questions. And additionally, start to micromanage some of the low-level issues that people really don't care about at the high level in order to keep the administrators of these systems from being overwhelmed with all the different pieces of a large system. And secondly, start to apply some of these techniques to a wider variety of systems, not just internet services, but say wide area distributed systems and networks, etc. So, thank you very much. If there are any questions? Yes? I'm sorry, could you repeat the question?
On the points to take away, we didn't have anything specific to internet.
Mm-hmm.
So I was wondering if you thought implications in
Mm-hmm.
or looking at faces or program.
There are some assumptions that we make, some properties of internet services that are important to the type of analysis that I'm doing. And here are some of them. One is that the component granularity is tied to the application functionality. And this isn't the case in all other systems. For example, if you were at the library level and looking at function calls in and out of a library, that is not necessarily tied to the functionality the library is providing. You often have helper functions, or you have some sort of interaction back and forth with the library to do a single function, etc. A second thing that internet services have that is very important to us is this large workload. This means that we get a good view, a statistically significant view of what the site is supposed to be doing in a relatively short period of time. And third, the fact that there's this common middleware platform that we can instrument allows us to start making application generic monitors as well. And in terms of whether this analysis would be useful in the context of other systems, you'd have to go back and revisit these assumptions and make sure that there's some compensating factor for them. Mm-hmm. Yes?
So you motivated this work by saying that it's rather complicated to write at development time.
Mm-hmm.
It looks to me that you still need to have quite close link to the code of the actual application. How can you get to the component level? How complicated is it to integrate that monitor into, let's say, Amazon?
Okay. So when there's the case of a common middleware underneath the platform, it's been relatively easy. So we've looked at J2E and specifically, that took the first cut at the instrumentation took on the order of days. And then once that was done, we didn't have to change any application code when we deployed a new application on top of this middleware. So in that case, it was pretty easy. Now, when you get into a site like Amazon.com, they have their custom middleware. They've developed things over time. And there you do have to go into their middleware and change it. And generally, it's much easier than changing the application code written on top of their middleware. So you still get a factor, order of magnitude improvement over actually asking them to change their source code. Now, in the case of Amazon.com, however, we didn't change their instrumentation. We took the existing log data and started analyzing it as well. So they already had a fair amount of logging for us to be able to analyze the system as well. So in the end, basically, if you're using something like J2EE or a system that's already instrumented with either commercial or custom instrumentation, then you don't have to change your application. In particular, you don't have to change this instrumentation as the application evolves. I think that's an important thing, as opposed to having a priori specifications about the application. Did that answer your question?
Kind of. So one thing I was wondering is you talked about this thing, rather application specific, how to choose to do. You choose too many,
Yes.
you have to monitor for days. You choose too few, you will not be able to detect all the behavior.
Mm-hmm.
So what level is say you did just for the middleware, that would imply that you don't need to do it on the application level.
The binning, so we chose to bin based on the URL, which was a relatively application generic binning function. It's not the best. In our case, for example, it didn't differentiate between the same request when a user was logged into the site or not logged into the site. So there's room for application-specific tweaking there. In terms of monitoring the site over a longer period of time, though, if you have enough workload coming in and you're seeing enough of a different variety of behaviors, it actually doesn't. You don't need to monitor for days and days, I think. Mm-hmm. Yeah.
So when, in the example, you move from pet store 1.1 to 1.3,
Mm-hmm.
could that be fixed by changing the time window or the number of bins?
Yes, that's actually something that I'm hoping to get a chance to look at while finishing up the writing of my thesis, is start monitoring some of the components that didn't get enough workload and monitor them for a longer period of time to see if we detect any significant changes in their behavior over a longer period of time, not just 5 minutes.
So, one of the so in your probabilistic context free grammar, in the example, it looks like the non-terminal nodes in the grammar correspond to components in the system. Is that always the case, or what were the non-terminals in the grammar?
Both the non-terminals and the terminals ended up being components in the grammar. So basically the path shape through the shape of the path through the system ends up being the equivalent of a parse through a probabilistic context free grammar, as opposed to a sentence.
About that, right? Because normally when you parse a sentence, the non-terminals are hidden. But in your case, you're actually told there is this non-terminal right here.
And the reason is because, and perhaps we can take this offline for further discussion, but the reason is that I wanted to keep the tree nature of the component call tree. And that corresponds directly to the parse tree, as opposed to flattening the calls out and then having then a tree generated behind it. But we can take that. Yeah.
All I meant by that was that as a probabilistic model, it's not really
Sure. Yeah, that I can understand that. Thank you. Yeah, a couple people stood up at 10. Sure. Yeah, some during the middle and some afterwards. Oh, it's fine. Oh, thank you. Let me wrap this up, I guess. Hi. Good, how are you doing?
Okay, thanks.
Yeah.
Thanks a lot for being there.
Oh, thanks. I'm sorry it took me so long. It's actually been 2 weeks since you sent the email. But
That's really helpful. Thanks a lot.
I'm glad. I hope something turns up. I gave them your email address directly and stuff, so I assume they'll contact you.
Is that the list of the
Yeah. Except for Amazon, because I think that probably they're not so research-oriented. I don't know. But otherwise, this are the people that I told you about earlier.
Okay.
Sure.
Thanks a lot.
I hope something... Hi.
Can we talk about this grammar?
Sure.
I'll be right back.
Okay.
So,
My name is Emre, by the way. Yeah.
I'm Tom.
Tom, nice to meet
I
you.
don't have a card.
Sure.
Um,
Are you at Microsoft or at the university?
I'm with Microsoft.
Oh, okay.
Yeah, I work here. So I'm in the machine learning group, and
Sure,
I do
great.
statistical inference and all that stuff.
Yeah.
So I'm really interested in models.
Mhm.
So my understanding is that to actually score a
Mhm.
call tree, in your case, it's
Oh,
very
I understand.
fast, right? Because
Yes.
you know all the calls that were made.
Mm-hmm.
So you don't have to use the expensive algorithms that people would normally use for parsing,
No.
which take n cubed time.
Yeah, I want to turn this off because it keeps getting into my eye. How to turn this off though?
Oh,
Preview.
gosh.
Follow.
Stage projector mute, I guess you
Oh,
can
there
do
we go.
if you want.
There we go. That's great. Otherwise, I kept looking at you and being blinded.
Oh, I see.
So
Because you can score these trees very fast,
Mm-hmm.
yeah, it makes me feel like this isn't really a grammar that you're doing. I mean, you're sort of using the mechanism of grammar, but as a model, it's not really a grammar.
Yeah, I'm not